you can see here, because we're defining the field as the force per unit charge, then this unit charge then cancels when we insert the Coulomb force law here. So that is the definition of the electric field. Basically, it's the force that will be felt at the point P. So this location Q is often called the source point, and P is the field point. We can define a unit vector R pointing in the direction from the source point Q to the field point P. In terms of R hat, the field E at P due to charge Q is given by this equation here. When Q is positive, the field is away from Q. When it is negative, the field is towards Q. Now suppose the field at point P is caused by several point charges, Q1, Q2, Q3, etc. at distances R1, R2, R3 from P, with associated unit vectors R1, R hat 1, R hat 2 from Q1 to P, and so on. Each unit vector points from its associated source point to the field point P. From the principle of superposition, it follows that the total electric field at P is the vector sum of the fields E1. If we got a point P and we got lots of charges all the way around it, it's just the sum of all of these. So you can see that's a basic principle of superposition. Quick example here. What is the electric field 30 centimeters from charge Q equals 4 times 10 to the minus 9? Well, the answer is, from Coulomb's law, the force on a test charge Q 30 centimeters from Q has magnitude 9 times, that's the K constant there, 4 times 10 to the minus 9 times Q, okay, over the distance between them. So F equals 400 newtons per coulomb times the Q. Then from the equation E equals F over Q, we have that the field equals F over Q, 400 newtons per coulomb. So that's the field. The direction of E at this point is along the line joining Q and Q dash away from Q. So that's just a really quick, easy problem. We're going to do another one now. Okay, this is how to calculate the torque of an electric dipole. These diagrams here show a structure incorporating 2-point charges, plus Q and minus Q. So that's a plus and that's the minus Q, having equal magnitude but opposite sign. So that's a plus charge and that's a minus charge, separated by a constant distance L. We call such a pair of charges an electric dipole. The electric charge distributions of many molecules, such as the water molecule, can be represented approximately as electric dipoles. In this diagram A, the dipole is in a uniform electric field E. The direction of E makes an angle theta, this angle here, with the line joining the two charges, called the dipole axis. A force F1 of magnitude QE in the direction of the field, and a force F2 of the same magnitude but in the opposite direction is exerted on the negative charge. The resultant force of the dipole is obviously 0. But since the two forces do not have the same line of action, they constitute what's called a couple. So we've gone over couples. The torque produced by a couple is the force times the this actual perpendicular displacement between the two lines of actions there, yeah? So to get that, we can simply use L and the angle, so that perpendicular distance is L sine theta. Force times this perpendicular displacement between the lines of action, okay? That's what torque is, okay, for this electric dipole. Since L sine theta is the perpendicular distance between the action line of forces. Okay, yeah, that's just what I've just said, basically. So if we look at here, we see there's an L here and there's a Q. Now if we take them out and think of them in isolation, the product QL of the charge Q and the distance L is called, they've given this a name, they've called it the electric dipole moment, and it's denoted by rho. Given that, The torque exerted by the couple is therefore this. Okay, so if we're concentrating, if we just treat this as the electric dipole moment, we don't actually write Q and L but write rho, then we can write this as rho E sine theta. Given this, we can also define a vector dipole moment, which is rho, which is vector rho. Okay, so now we can define a vector torque, yeah, as the dipole crossed with the vector of the electric field. This torque tends to rotate the dipole to a position in which rho is parallel to E. In other words, we end up with this situation here. In this position, the torque is 0, and if E is uniform, the dipole is in equilibrium. So that's really the description of electric dipole and how you calculate the torque on it.